Good morning, sixth grade. Hopefully everybody had a great spring break and we're getting ready to start back with math again. Today we're starting on chapter 11, lesson 3, Polygons. So to get your notes there, go up into your Google Classroom, scroll over to your classwork, go down here to chapter 11, click on that, and you will find your notes here in the completed notes section of the Google Classroom. So let me pull up my notes here. Okay, so here we go. We have our notes here. Today we're going to start chapter 11, lesson 3, Polygons. Pretty easy today. So just follow along. Well, the first thing we're going to do, we're going to talk about how do we classify our polygons. Is it a polygon or not? So let's determine if these shapes are polygons or not. So let's look at the definition here. With the definition here, it says a polygon is a simple closed figure. That's going to be very important. Formed by 3 or more line segments. Extremely important, called sides. The figures below are not polygons. So let's talk more about this. Let's see why they are not a polygon. So if we take a look here, if we look here, this figure is not a polygon because we have a curve here. And we said in the definition, a polygon must be made up of line segments. When it's curved, that's not a segment. So we would say, hey, this is not a polygon. If we take a look here, now it does not say this in the definition, but we cannot have any type of an overlap like what you see here, okay? This actually breaks it into 2 of our polygons here, not 1. So this overlap, this cross right here, then says, hey, this is not a polygon. Now, this last one here, it says, if we have here, it's a closed AF figure. This is not. It is open. It had these 2 pieces here have not been connected at all. So these are basically the 3 things of why these are not our polygons here. So 1, because this one has curves. 2, because it's overlapped, and 3, because this is not closed. So now let's look at classifying these polygons. How do we name them? We name them according to their sides. So as you can see here, the smallest polygon that we can ever have here is a triangle, because in our definition, it says formed by 3 or more. So the smallest one the smallest polygon that has 3 sides is a triangle. Now, there's different types of triangles. There's our scalene, there's our obtuse, there's the acute, there's the isosceles, equilateral, equal angular. So there's a bunch of different types, okay? But we're basically just going to say, hey, this is a basic thing, a polygon that we're talking about. So with 3 sides, it's a triangle. 4 sides, a quadrilateral. 5 sides, pentagon. 6 sides, hexagon. 7 sides, heptagon. 8 sides, octagon. 9 sides, nonagon. And 10 sides is a decagon. These are the basic eight ones that you are going to need to know. So let's look at some of these examples here. Let's determine, first of all, are they a polygon? If so, how do we classify them? If not, why? So if we take a look here, let's look here at our first one here. Is it made up of our segments? Yes, it is. Is it closed? Yes. Is there anything overlapping? No. So yes, this is a polygon. It has 1, 2, 3, 4, 5, 6, 7. It has 7 sides. So 7 sides is a heptagon. Now, we would actually call this a concave heptagon because we have a side that's been pushed in, okay? Like you're going into a cave. Since it's pushed in, if I were to connect these 2 edges right here, we can see that this side down in here has been pushed in. That's why it's concave and not convex. Over here, well, we have our segments here. That's good to go. No overlapping. It is closed. So yes, it is a polygon with 1, 2, 3, 4, 5 sides. So it is a pentagon. Very good. Let's continue to scroll on down here. Let's look at this here. First of all, is it made up of line segments? Yes, it is. Is there any overlapping? No. Is it closed? Yes. So 1, 2, 3, 4, 5, 6. 6 sides. This is a hexagon. This is a concave hexagon. Let's look here at the last one here. Look what we have here. We have a curve. Automatically, when we see that curve, it is not a polygon because it has a curved side. Okay, so now what we're going to look at is how do we determine how many total degrees are inside do the interior angles of a polygon do they have? Now, if you remember, we talked about before. Let me just pull this up here. We talked about this before. When we're dealing with a triangle, okay, if I put a triangle here, we know that there are a total of 180 degrees in a triangle, okay? 180 degrees, okay? So if I take this angle plus this angle plus this angle, it will total 180 degrees. Well, let's look at another example. How about a rectangle or a square or a trapezoid? Well, those are quadrilaterals because they have 1, 2, 3, 4. Well, let's just take this example of our square here. Well, a square has 4 90-degree angles here. 4 90 degrees here, which is 90 plus 90 plus 90 plus 90, or 90 times 4 is 360 degrees. So all quadrilaterals have 360 degrees. Now, what about a decagon? Well, that's going to be a little bit more difficult to figure out. So that's why we use a formula. So let's see what we have here. So it says the sum of the degree measure of interior angles of a polygon with n sides, that's the number of sides that it has, is the formula, and in parentheses n minus 2 close our parentheses times 180 degrees. Okay, so there is a way where they can say, okay, break this up into triangles. See how many triangles you have, and then take the number of triangles that you have and multiply it times 180 degrees. Let's don't. Let's just look at this, okay? We know that a triangle, let's just start with a triangle, okay? We'll use this as our example here. We know that a triangle has 3 sides. So we know it has 3 sides, okay? So if we plug this into our formula here, we'll have our parentheses, 3, that's the n, that's our number of sides, minus 2, this is always our constant, it's always minus 2, times 180. Okay, so if I do 3 minus 2 is 1, 1 times 180 is 180 degrees. So no matter what type of triangle you have, there's going to be a total of 180 degrees. So let's look here at some of these examples down here. Okay, so it says, find the sum of the measures of the interior angles of a nonagon. Well, we know that a nonagon contains 9 sides. Since it contains 9 sides, we do our formula n minus 2 times 180. So I have it right here. N is 9. So 9 minus 2 times 180. So 9 minus 2 is our 7. 7 times 180 is 1,260. So yes, in a nonagon, no matter how you draw this nonagon, there's going to be 1,260 degrees, a total of the interior angles in a nonagon. Well, let's look at a heptagon now. Okay, find the sum of the measures of the interior angles of a heptagon. So we know that a heptagon has 7 sides. So we want to see what is the total degrees of the interior angles in a heptagon. So we use our formula, n minus 2 times 180. So we have 7, which is our n, minus 2 times 180. So 7 minus 2 is 5. 5 times 180 is 900 degrees. So in any heptagon that you draw, that you make, it will have a total of 900 degrees. Now, what if they want to figure out what one of the measures? Now, these have to be regular, our polygons, which means if it's regular, that means all the sides are the same length, and all the angles are the same number of degrees. So it says find the measure of one interior angle of a hexagon. It really should say of a regular hexagon, because we want to make sure that all of the angles are the same and all the sides are the same. So let's use our formula. So we're going to do one little piece that's different at the end. So if we take a look here, we know that our hexagon has 6 sides. So we plug it into our formula. N minus 2 times 180. So 6 minus 2 is 4. 4 times 180 is 720. This 720 represents the total number of degrees in a hexagon, okay? There's a total of 720 degrees. Now, if we want to figure out what one of those degrees is, what one of those angles, what is its measure, okay? What we're going to do, we're going to take the total degrees that we have here, the 720, and this time we're going to divide it by 6, because there's 6 of the angles, the angles in a hexagon, okay? So 720 degrees divided by 6 is 120 degrees. So each angle in a regular hexagon is 120 degrees. Okay, so let's talk about a stop sign. So the stop signs that you see when you're driving with your parents, those are regular octagons, which means all the sides are the same length, all the interior angles have the same measurement. So what is the measure of one interior angle in a stop sign? So we know that the octagon has 8 sides. We use our formula, n minus 2 times 180. So 8 minus 2 is 6 times 180 is 1080 degrees. So the sum of the interior angles in an octagon is 1080 degrees. Now they just want to know what is the measure of one of those degrees, of one of those angles. So we have to take our 1080 divided by 8, okay, which equals 135 degrees. So each angle in a regular octagon is exactly 135 degrees. Okay, look here, last couple of examples here. It says a repetitive pattern of polygons that fit together with no overlapping or holes is called a tessellation. Okay, the sum of the measures of the angles where the vertices meet in a tessellation is 360 degrees. What they mean by that, okay, what they've done, they've taken this square, they've connected it to that square, to this square, to that square, and then they said, okay, it doesn't matter what tessellation you have, these angles here, this angle here, this angle here, this angle here, this angle here has to add up to 360 degrees, which it does. Now look at this one here. These are made up of 45-degree triangles here. So this is 45, 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 that is 45. So I have 8 45-degree angles here where they all come together at one point. Because we have 8 45-degree angles, 8 times 45 is 360 degrees. So as you can see here, these tessellations, the sum of the measures of those angles where the vertices meet will always equal 360 degrees. So we're going to determine, hey, is this a tessellation or not? So let's look at these examples down here. It says, determine whether or not a tessellation can be created using regular hexagons. If not, explain. Okay, so let's take a look here. We have a hexagon. A hexagon has 6 sides, okay? So we're going to plug it into our formula, n minus 2 times 180. So 6 minus 2 is 4. 4 times 180 is 720. So we know inside one hexagon, okay, if we were to add up all of the angles in the interior angles inside a hexagon, we would get 720 degrees. So let's see what each angle is. Okay, so each angle here, if we take our 720, we divide it by 6 because hexagon has 6 sides. We know that each interior angle of a regular hexagon, each interior angle is 120 degrees. Okay, so we want to see, hey, can we take a certain number of hexagons, put them together at one point to see if the angles will equal 360 degrees. Well, here's how we do that. We take our 120 degrees, which is the measure of one interior angle. We do 120 ends because we have to see how many of these can we put together to equal our 360 degrees. If it comes out as a whole number, then it makes a tessellation. If it does not come out to be a whole number, it is not a tessellation. So we take our 120 n equals 360. So in order to get n all by itself, I'm going to divide both sides by 120, divide 120 here, divide 120 here, divide it out, n equals 3. So yes, that is a whole number there. Since 120 degrees divides evenly into 360 degrees, you can use a regular hexagon to make a tessellation. Okay, well, let's look at this next one over here. Determine whether or not a tessellation can be created using a regular decagon. If not, explain. Okay, we know that a decagon has 10 sides. So we'll use our formula, n minus 2 times 180. So 10 minus 2 is 8. 8 times 180 is 1,440 degrees. So the total degrees of the interior angles of a regular decagon is 1,440 degrees. So we need to see what each angle, what its measure is. So I'm going to take my 1,440 degrees, divide that by 10 because it has 10 sides, which gives me 144 degrees. That is the measure of each angle inside the decagon. So I take my 144n, okay, equals 360. So we're trying to see how many of these decagons can I put together to equal 360 degrees. So I got to get the n all by itself, divide both sides by 144, divide by 144. So n equals 2.5. So the answer is no, because this number here, this 2.5 is not a whole number. So that means we cannot make a tessellation with this. It says here, since 144 degrees does not divide evenly into 360 degrees, you cannot use a decagon to make a tessellation. Remember, it must be equal here. So hopefully you understood everything that we talked about today. If you were confused with anything, please review the video lesson or get a hold of me, email me. But other than that, guys, work on your homework today. Homework is down here at the bottom. Check your answers. And tomorrow we'll be starting on 11-4. Have a great day, guys. See you tomorrow. Bye-bye.